In this video, we're going to talk about 8.3, trigonometric integrals, and our objectives will be to solve trigonometric integrals using powers of sines and cosines, solve trigonometric integrals involving powers of secant and tangent, and to solve trigonometric integrals involving sine, cosine products. So let's go ahead and get started here with our procedures for trigonometric integrals. So three big things that we want to think about is that I can take the derivative of sine to get cosine. I can take the derivative of cosine to get negative sine. So sine, cosine integrals are going to be the easiest ones to think about. So big category number one is sine and cosine. Big category number two is that the derivative with respect to x of tangent is equal to secant squared. I can also think derivative of cotangent is going to be a negative cosecant squared. So it's going to be something here related to tangents and even powers of secant, or cotangents and even powers of cosecant there that I'm going to be interested in. The last one that I'm interested in is that the derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent. So I'm going to have an odd power of cosecant and cotangent on this one, or an odd power of secant and tangent to save that, to have that be part of my du. So I'm looking for what's u and what's du and those types of things here. These are my primary things that I'm looking at. So let's break this down for integrals involving powers of sine and cosine. Powers of sine is odd and positive, save one sine factor and convert the remaining factors to cosines, and use a u substitution, u to the n, du, expand and integrate. Likewise, if we have powers of cosine as odd and positive, save one cosine factor and convert the remaining factors to sines using u substitution, expand and integrate. If both of them are odd, just pick one. I like picking sines to be to the nth power if I have the choice, because then I don't have a negative in my du. So if both sine and cosine are even and non-negative, you have to use power reducing formulas, which we'll have later in the notes. Repeat as necessary to convert to an odd power of cosine, and then proceed with 1b. If you have integrals involving secant and tangent, if the power of secant is even and positive, then save a secant squared factor and convert the remaining factors to tangents, and use a u substitution of tangent being u to the n, and then your du is going to be the secant squared part. Expand and integrate. If your power of tangent is odd and positive, save a secant tangent factor and convert the remaining factors to secants. So again, derivative of secant is secant tangent. So that's the third type here. So we're talking about type 2 and type 3 right there. If you have no secant factors and the power of tangent is even and positive, convert a tangent squared factor to a secant squared factor using your Pythagorean identity, and expand and repeat as necessary until you get just one secant squared, until you get all of your integrals taken care of. Your last one that's going to have a tangent left, you're going to be able to write a sine over cosine and you're going to be able to use your ln property for that. We did 2D last time in the notes, but we're going to do it again when the integral of secant to the m dx for m is odd and positive. Use integration by parts. If 2a through d do not apply, convert to sines and cosines and refer back to number 1. If you can't find something to do here in rule 2, you can always change your secants and your tangents to sines and cosines and go back and look at 1a through c. Integrals involving sine cosine products use the product to sum formulas that we're going to have in the notes later. So let's go ahead and get started here. We're going to illustrate these in order. So we have an odd power of sine and we have an extra cosine left over. U is equal to sine x, du is equal to cosine x dx, n is equal to 5. This is going to be u to the 5th du. We're going to make that 1/6 u to the 6th plus c, and that's 1/6 sine 6th x plus c. So let's go ahead and look at number 2. We have an odd power of sine, an even power of cosine. So let's go ahead and leave the extra sign here, change everything else to cosines. So this is going to be a sine x dx over here for du, sine squared, 1 plus cosine, sine squared plus cosine squared is equal to 1. So if I want to solve for sine squared is 1 minus cosine squared. So this is a sine squared cosine to the 4th right now. I pulled the other sine out over here to be with du. Cosine to the 4th times sine squared is 1 minus cosine squared. And leave all this over here as part of du. So this is cosine to the 4th x sine x dx minus 4 and 2 is 6 sine x dx. And so derivative of cosine is a negative sign. So we need to fix that here. Negative and negative and negative, and that will make that positive. So this is going to make this negative cosine to the 5th x 1/5. This could be positive 1/7 cosine to the 7th x plus c. Right? Illustrating 1b, where power of cosine is odd and positive. I actually used 1b up here. So, but let's do that again here. So I'm actually going to switch this one and make this one a 1a, and I'm going to make this one here a 1b. Dealer's choice, because I could have chosen either one, and I like this one as a 1a better because there's my du right there. So this is going to be cosine to the 6th x is 1/6 plus c. So I don't have to convert anything like that. This one here, we have an odd power of cosine that we need to save one of them. So let's save a cosine x dx over here, and we have a cosine to the fourth x and a sine squared x. So change these cosine to the fourth. We're going to make cosine squared x equal 1 minus sine squared x. Cosine to the fourth. X is cosine squared squared. So that's going to be 1 minus sine squared squared. So cosine to the fourth x is going to be 1 minus 2 sine squared x plus sine to the fourth x times sine squared x. Multiply from this side times cosine of x dx. So we get an integral of sine squared x cosine of x dx plus an integral of minus 2 times the integral of sine to the fourth x cosine x dx plus an integral of sine to the sixth x cosine of x dx. So this is going to be sine u is going to be equal to sine of x. Du is going to be cosine of x. It's all of them are already set up that way with a u to the n du. So this is sine cubed x, 1/3 of that, minus 2/5 sine to the fifth of x, plus 1/7 sine to the seventh of x, plus c. Right? Moving on here, we have a power of cosine that we're going to save one of them and change the rest to sines. Our power on sine right now, and when we bring that denominator up to the numerator, is going to be a -1/2 power on sine. So this is pi over 6 to pi over 3. And this is save a cosine. Then we have a cosine squared is a 1 minus sine squared x over, and then this is the square root of sine of x. So this is going to be pi over 6 to pi over 3 sine of x to the -1/2 power times cosine of x dx minus integral 2 minus 1/2 is 3/2 cosine of x dx, like so. So we're going to have sine of x to the +1/2 power divided by 1/2 is the same as multiplying by 2 minus sine of x to the 5/2 power times 2/5. All of this evaluated from pi over 6 to pi over 3. Let's think about our unit circle for a second, or our trig triangles. If we have pi over 3, that's going to be √3 over 2 for sine. So this is 2 times √3 over 2 to the 1/2 minus 2/5 of √3 over 2 to the 5/2 minus 2 times 1/2 to the 1/2 plus 2/5 of 1/2 to the 5/2. That's pretty gross. That's our exact answer, whatever that is. And if we want to approximate that, that's 0.2385. Let's now move on to illustrate 1C, where we have even powers of both sine and cosine. So, or we have only an even power of sine or only an even power of cosine. We need to use a power reducing formula. So our power reducing formulas are right here. And we're going to have to use this one since we have even powers of cosine. So let me write that down up here. Cosine squared theta is equal to 1 plus cosine of 2 theta over 2. And I'm going to have to do that twice. So cosine to the 4th theta is 1 plus cosine of 2 theta over 2 quantity squared. Cosine to the 4th theta is, it's going to be over 4, 1 plus 2 cosine 2 theta plus cosine squared 2 theta. And I'm going to have to apply that cosine squared formula again. So this is cosine to the 4th theta is 1/4 plus 1/2 cosine of 2 theta plus 1/4 of cosine squared of 2 theta. So cosine to the 4th theta is equal to 1/4 plus 1/2 cosine of 2 theta. Let's make these x's before I get too far. X, 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 X. So plus 1/4 times, now cosine squared is going to be 1 plus cosine double this angle. So that's going to make that 4x over 2. So cosine to the 4th x is equal to 1/4 plus 1/2 cosine of 2x plus 1/4 times 1/2 is an 1/8 plus 1/4 times 1/2 is an 1/8 of cosine 4x, like that. So this is going to be 2/8, and an 1/8 is going to be 3/8 plus 1/2 cosine of 2x plus 1/8 of cosine 4x dx. So this is 3/8 x plus 1. Just split this up this way before I start integrating. 3/8 integral of dx plus 1/2 integral cosine 2x dx plus 1/8 integral cosine 4x dx. All right, so this one, easy enough. That's 3/8 x. Now I need a times 2 in here to complete my du, which means I need another 1/2 out there. I need a 4 in here to complete my du, which means I need to multiply by a 1/4 out there. So that's plus 1/4 of sine of 2x plus 1 over 32 sine of 4x plus c. There's lots of side work over there to expand that integral on that one. So memorize those power reducing formulas, especially sine squared and cosine squared. We'll be using them a lot. Tan squared we don't use nearly as much, but it's important to know that one, that it's this numerator divided by this numerator, because tangent squared is sine squared divided by cosine squared, and the divided by 2's will get rid of each other. Right? Moving on and illustrating 2a, when we have even power of secant and an odd power of tangent. We want a tangent, power of tangent, and save a secant squared. So I'm going to save a secant squared x dx over here. That leaves me with a tangent cubed times a secant squared here. 1 plus tangent squared is secant squared. So tangent, so I'm going to change that secant squared into a 1 plus tangent squared. That gives me a tangent cubed x secant squared x dx plus a integral tangent to the 5th x secant squared x dx. So that's going to give me 1/4 tangent to the 4th x plus 1/6 tangent to the 6th x plus c. All right. Now we need to have u be equal to secant, and we need a secant tangent. So let's go ahead and see if we can make that come up here. So this right now is tangent to the 3rd x times secant x to the -1/2 dx. So we want to multiply by a secant over a secant. Because we need a secant and a tangent in the numerator, and we have that secant trapped inside of the square root sign. We can't use that one. So we need divided by secant x. We're going to have a tangent squared x left here when we save a secant x tangent x dx over here. And we're also going to have the secant x to the -1/2 right here. So let's see what's going to happen with all these secants when we change these tangents to secants. Using 1 plus tangent squared equals secant squared. That's going to be tangent squared is equal to secant squared minus 1. So this is secant squared minus 1 times secant to the, really this is going to be -3/2 now up here. And so this is going to be secant to the 2 over 1 minus 3 over 2 x minus, and this is times secant x tangent x dx, secant x tangent x dx, minus integral of secant x to the -3/2 times secant x tangent x dx. So this is 2/2. That's 4/2 minus 3/2 is secant x to the 1/2 times secant x tangent x dx minus integral of secant x to the -3/2 times secant x tangent x dx. I don't know about you, but I'm ready for some u substitution to stop writing all of that. So u is equal to secant x and du is equal to secant x tangent x dx. So this is going to be u to the 1/2 du minus the integral of u to the -3/2 du. This is going to be u to the 3/2 times 2/3 minus u to the -1/2 times a -2 plus c. Be 2/3 u is secant x to the 3/2 plus 2 secant x to the -1/2 plus c. I really want to factor that here if I can, but I guess I'll just leave that for now. If I had made a common denominator here, I'd get I'd probably get something fun and interesting, but let's just leave it right there. So let's go ahead and look at 2c, which is when the power of tangent is even and there's no secant factors. We need to use the fact that tangent squared x plus 1 is equal to secant squared x, and 0 pi over 4. So we have a tangent squared x times tangent squared is secant squared minus 1. Like that. We have a 0 and a pi over 4. We have a tangent squared x secant squared x dx, and that's awesome because the derivative of tangent is secant squared minus integral from 0 to pi over 4 of tangent squared x dx. So we're going to have to do that again. We're going to get 0 to pi over 4 tangent squared x secant squared x dx minus 0 to pi over 4 of secant squared x minus 1 dx, 0 to pi over 4 of tangent squared x secant squared x dx minus the integral 0 to pi over 4 of secant squared x dx. That's perfect because that's an exact antiderivative, plus 0 to pi over 4 of 1 dx. That's amazing as well. So this is 1/3 tangent cubed x from 0 to pi over 4 minus tangent of x from 0 to pi over 4 plus x from 0 to pi over 4. Tangent of pi over 4 is 1. This is 1 cubed minus tangent of 0 is 0 cubed minus 1 minus 0 plus pi over 4 minus 0. This is 1/3 of 1 minus 1 plus pi over 4. So this is going to be 1/3 minus 1 is a negative 2/3 plus pi over 4, or pi over 4 minus 2/3 if you prefer. And that is approximately 0.119. Now we did do this one last time, but I'm going to go ahead and do it again because people may be watching this video to see how to do this and may not be looking back at the integration by parts video. So when you have an integral involving powers of secant and tangent, where the power of secant is odd and positive all by itself and there's no tangents, use integration by parts. We set that up last time. Remember, integration by parts says that the integral of u dv is equal to uv minus the integral of v du, like that. So we're going to remember that this one wraps around. So I'm going to call this I for the integral that I'm looking for. And so I is going to be equal to, and I'm going to let u be equal to 1 of the secants, and dv be equal to the secant squared x dx, because this is the exact derivative of tangent. And that makes u equal to secant x tangent x. So using this substitution right here, my integral is equal to u times v is secant x tangent x minus the integral of v du. It's going to be secant x tangent squared x dx. And I need to use the fact that 1 plus tangent squared is equal to secant squared. So tangent squared is equal to secant squared minus 1. Right, and then that again right there is I. So I equals secant x tangent x minus I plus, and then this is one of our forms we learned in Calculus 2 with Chapter 5. This is ln of the absolute value of secant x plus tangent x. So we're going to get these i's on the same side. I haven't added my constant of integration yet because I haven't completely solved for I. So I is equal to 1/2 secant x tangent x plus 1/2 ln of the absolute value of secant x plus tangent x plus c. And so secant cubed x dx is equal to 1/2 secant x tangent x plus 1/2 ln absolute value of secant x plus tangent x plus c. Let's go on and look at 2e, which is integrals involving secants of powers of secant and tangent, where a and e don't work and we want to convert to sines and cosines. There's no nice way to do this problem, so I'm going to make this a 1 over cosine divided by a cosine, a sine squared over cosine squared. And that's going to be a 1 over a cosine times a cosine squared over a sine squared. That's going to be cosine up here. And that's going to be a 1 over sine squared. So sine x to the negative second power cosine of x dx, like that. And u is equal to sine x. Du is cosine of x dx, and n is -2. So we're going to get sine x to the negative first divided by -1 plus c is a negative cosecant of x plus c. Alternatively, when we got to this point, we could have called this a cosecant cotangent. And we got here to cosine over sine is cotangent and 1 over sine is cosecant. And we need a negative cosecant cotangent to be the exact derivative of cosecant. So that's a negative cosecant x plus c. That's another way to do that one, but our instructions told us to convert everything to sines and cosines and to use our rules for sines and cosines at that point. All right, so now number 3, where we need product to sum formulas. So if we have the product of sine of mx and sine of nx, that's 1/2 of cosine of the quantity m minus nx minus cosine of the quantity m plus nx. And hopefully that simplifies it down for us. If we have sine mx cosine nx, we have 1/2 of the quantity sine m minus nx plus sine m plus nx. And we have cosine mx cosine nx. That's 1/2 of cosine m minus nx plus cosine of m plus nx. So this one is the same thing if we see cosine written first, but remember cosine keeps the n and sine keeps the m. So even if they switch places, cosine has n and sine has m in that second rule. So let's look here. We have a sine times a cosine here. So m equals 5, n equals 4. We're going to rewrite this as 1/2 of, let's just put the 1/2 on the outside, sine of 5 minus 4 is 1x plus sine of 5 plus 4 is 9x, like that, dx. This is 1/2 sine x plus 1/2 integral dx plus 1/2 integral sine of 9x dx. This is going to be 9 and 1/9 there. It's going to be negative cosine right there. And this is going to be 1/18th. And this is going to be a negative cosine here. Plus c. And that's our last example for this video. We'll come back next time and talk about 8.4 with trigonometric substitution. See you for the next video.